Question 24, determine if this guy converges or diverges. And again, we're going to use the comparison test. So if you look at this one, if you'll check this out, we got basically 7/4 x squared, okay? 7/4, this reduces to 7/4 times 1 over x squared. And so what I'm going to do on this is I'm going to compare this to 5 over x squared. The reason I picked 5 over x squared is because it is bigger than 7/4, 7 over 4x squared, okay? 5 over x squared is bigger. So what I'm going to do is I'm going to look for a situation that matches this guy, okay? Where I'm picking an equation that's larger. I want to show that it converges, and if that converges, this guy right here will converge. So that's what I'm going to do. Okay, how's it look? Looks like this. We're going to set up our limit as b approaches infinity of the integral from 1 to b of 5 over x squared, or 5 times x to the negative 2. When I integrate that, I end up with 5 times, let's see here. Yeah, 5 times x to the negative 1 divided by negative 1, evaluated from 1 to b, which is the same thing as negative 5 over x evaluated from 1 to b. When you evaluate an integral, it's stop minus start. So this is going to be negative 5 over infinity minus negative 5 over 1. Now, when we look at this guy right here, he's going to go to 0 because it doesn't matter what you do. If 5 never changes and the bottom of the fraction gets bigger, then this guy is actually going to approach to and go to 0. Okay, this guy's going to go to 0. That just leaves us then with this part right here, which is going to be 5. So since this one converges and it's bigger than this guy, he also converges. And that's all there is to it. Okay, find the volume of the solid generated by revolving the region under the curve y equals 2 over x from x equals 1 to x equals infinity around the x-axis. So let's just real quick get an idea of the shape that we're talking about here. And it's basically going to be really similar to the line y equals x. So in that first quadrant, we're looking at something that does like this. Okay, and we want to look at the part of the curve that starts here at 1 and moves towards infinity. Okay, so we're trying to find the volume of the shape of a curve that's revolving around the x-axis that goes on forever and ever and ever. And that sounds really difficult. Like, how in the world are we going to do that? Well, here's how. Remember, we don't need that. Remember, when you rotate around an axis to find volume, then you look at the shape that you would get by making a vertical slice. So if I pick any point on this curve, y equals 2 over x. If I pick any point on that curve, as it moves around the x-axis, it creates a circle. And so the radius of that circle, which is from the center of the circle to a point on the circle, is going to be whatever the y-coordinate is that matches the x-coordinate at that point. So what we're talking about is a circle, and the area of a circle is pi r squared. The r in this case is going to be our equation 2 over x. What we're going to do then is look at the integral from 1 to infinity then of the area of a slice of this graph. So that's going to be pi times r squared. Well, this doesn't look too bad, actually. We can handle this. We've been working with improper integrals through this whole section. So we're going to just make our little change to limit form here. We're going to look at the limit as b goes to infinity of And notice 2 squared is 4, and in pi, those are constants, so I can put them in the front. 4 pi times the integral from 1 to b of 1 over x squared dx. 1 over x squared is the same thing as x to the negative 2 power. So when I integrate x to the negative 2, let's just run over here real quick and look at the integral of x to the negative 2. Remember, this is going to be x to the negative 1 divided by negative 1, which is negative 1 over x. That's what this integral goes to. So back over here to this guy, I'm looking at the limit as b approaches infinity of 4 pi times where I stop, which is b, so negative 1 over b, minus where I start, which is 1, so negative 1 over 1. And I run this guy through right here. Well, as b goes to infinity, right here, as that guy goes to infinity, the bottom gets large, the top never moves, we go to 0. So this first term, he goes all the way to 0. All right, that just leaves us with 4 pi times 1, which is going to be 4 pi units cubed. And that's how you find the volume. And even though we have a situation where we're going on forever, we're growing larger and larger and larger with our x values, the area underneath that curve that we're revolving around the x-axis just gets so small, so small, so small that we can't really determine a number of any significance from that. So basically what we're doing is we're looking at this improper integral, we're allowing the math and calculus to take care of some of those more tricky things for us, and we're able to determine without a shadow of a doubt that this shape right here, y equals 2 over x, has a finite volume over an infinite length. Pretty cool, huh?